for a sustainable energy future. As a disclaimer, before I introduce our speaker today, further introduce her, I would like to let you know that this webinar will be recorded, but not the questions and answer part. So for that, feel free to question without any pressure of being recorded at all. And this webinar will be available on the online platforms and YouTube of the Dutch section of the Combustion Institute. So without further ado, I fully introduce you now, Dr. Giulia Finotello, who is an assistant professor in the mechanical engineering department at the Eindhoven University of Technology. She holds a degree in chemical engineering from the Polytechnic of Torino and gained early industry experience during an internship at BASF in Germany. She completed her PhD at TUE, where she investigated droplet collision dynamics in a spray dryer, combining experiments with simulations in collaboration with Tetra Pak in Netherlands. Dr. Giulia Finotello's research focuses on iron powder as a circular energy carrier, including the first ever cyclability study on iron powder reduction and oxidation. She leads the powder production and processes laboratory, where her team explores atomization, spray technologies, and metal fuel reduction as part of the metal fuel cycle. And her pioneering research on iron powder regeneration earned her a prestigious grant from the NWO Open Technology Program for the CIRCL Circle project, which includes major collaborations with Shell, Rift, and Metalot. And beyond her research, she's an active organizer of international scientific events, a course developer in chemical engineering education, and she is also a member in the scientific managing team of the Eindhoven Institute of Renewable Energy Systems, IRES. So let's give a warm welcome to Dr. Giulia Finotello, and thank you for accepting our invitation to present today.
Well, thank you very much, Claudia, for the invitation. I hope you can see my screen and hear me well. Yeah?
Yes. Yeah.
So thank you again for the warm introduction. Indeed, today we are going to talk about something a little bit different than the usual Combustion Institute webinar. Indeed, we are looking into the reduction and cyclability.
One second, Giulia, you got muted.
Oh, can you hear me now?
Yes.
Yeah,
yes.
I didn't mute myself.
I think it muted by itself. Yeah, no worries. Okay. Go ahead. Yeah.
So of course I need to introduce first the cycle, and I think that you've seen already many times this picture from a previous talk, such as the one from Professor Philippe de Gouy and also Professor Cheng Mi. They are colleagues, and I'm working with them on the iron power. So, and their talk focus more on the combustion part. So on this side of the cycle, we are combusting metal powder of the typical size of a micron. This releases heat at high temperature that can be used in an industry application, for example. And you can see here that is a very good clean exhaust because we have zero production of CO2 emission and very low production of other compound like NOx. But what I'm focusing more is this side of the cycle. So actually the iron oxide regeneration back to iron, and that this can be done through different processes. The process that you see here of reduction uses hydrogen. Of course, to make this cycle CO2 zero emission, you need also to use renewable energy input for the production of this hydrogen. And in this case, you can see also that if you do reduction with hydrogen, you also produce water vapor that can be, for example, used back to produce hydrogen. So, so from my colleagues, I just show a picture here of a very beautiful tornado combustor that my colleagues developed. And then here for the reduction side, you can see at the top of a fluidized bed, what you see is this bubble that are the gas that is coming from through the particles. So the particles are mixed, and the heat and mass transfer is enhanced by this mixing and this motion of the bed. And what you see here is just the tube for the thermocouple into the reactor, nothing strange. Okay, and what are the key benefits of this iron powder? As I said, again, we see it as a sustainable energy carrier because especially for iron, we can release chemical energy, but we can also collect back the powder in the solid state so that can be regenerated. So that's really used as a sustainable energy carrier. As I said also before, we have no direct CO2 emission. And we can produce heat for industrial processes due to the fact that also iron has a high energy density. Another component of this cycle is that it's a circular process, and well, we know that we've seen this is a cycle, but it's actually something that needs to be demonstrated, and it's something that I will talk about also in my talk later on. So let's get more into the reduction processes that are available. We know already from steel making industry that direct reduce iron. So this is already done in a shot furnace where we have a solid state reduction of the iron oxide. So we, in these very large facilities, pellets and lump ore are introduced, and the reducing agent can be hydrogen or hydrocarbon mixture with CO and hydrogen. Temperature are relatively high, and what we produce here is direct reduced iron or sponge iron, which is called like this because what you produce is a very porous iron ore, and you can see even from the picture, you can even see larger cracks. So it's very porous. So something is already done. It's indeed one of the techniques that are used to regenerate mostly pellets, so larger pellet. And here I give an overview of all the steel making technology that are current available solution. So that's I'm not discussing here the very low TRL niche technology for now. And this is an overview that puts all these alternatives. So we have a shaft furnace here, and we have the technology readiness level here. Together with other properties. But what is important to see is that while the shaft furnace is already used widely and it has a high technology readiness level, then below we have the fluidized bed reduction. And then you see that we have other three techniques. The suspension iron making technology, which is occurring at very high temperature, so that the reaction can go very fast, but the technology readiness level is lower. And the same goes for the plasma reduction and for the electrochemical reduction. So we are talking about TRL, which are much lower than a fluidized bed and shaft furnace. So if we look at all these technology, of course, there are pros and cons, and we will have a look at these pros and cons for all these technologies. What you can think, what you see here is this technology are put here in perspective for increasing time. So if you increase the time, your reduction rate increases. So you can do reduction faster. You see here that we pass from reduction time of days to millisecond. So that the reduction time it's decreased a lot. And And of course, we can think of, so if we look at energy efficiency and reduction rate, we can think that maybe there is an optimum of this technique. However, it's very difficult to put such an optimum of one technique. And also, if we do this and we tend to exclude one of the techniques, it means that we are limiting our possibility to really look into what we can do to regenerate iron oxide, both for the iron cycle as well as the steelmaking industry. So the approach that we are having at TUE is actually looking into all this technique, and it's a work that I'm doing together with my colleagues. First is we are doing a reduction with hydrogen in fluidized bed. So we are feeding combusted iron that you can recognize here from their very spherical shape, very solid. And what we produce is similar to the DRI picture that you've seen before. Is a very porous solid particle. And in this case, what we need is hydrogen and high temperature heat. So I'm talking about temperature between 500 and 900 degrees Celsius. And here we have some of our fluidized bed at the university of different scale and type. However, we are looking into also the electrochemical deposition. So this is a totally different technique. An alkaline solution is with suspended particles is used, and with electrochemical process, you have deposition of iron at the cathode. And the typical picture is this iron deposit is typically of this crystalline structure. And in this case, you do not need any hydrogen, but you need, of course, electricity and low temperature heat. We are not going above 100, 110 degrees because, of course, we don't want the evaporation of the suspension of the aqueous alkaline solution. And I will briefly also touch on that later. We are doing that in the parallel plate, a very simple but very effective electrochemical cell. And we are also developing rotating disk continuous reactors to help with the scale up. We also started very recently with my colleague Giulia and me, the flash reduction. So this is a process which occurs at very high temperature, and so we are talking a very high temperature where you can reduce the reduction time of a second. We can do it with resisted heating. Indeed, we are developing a drop tube reactor where we have resistant heating, and we want to do very controlled experiment to look into the kinetic of a reduction at such a high temperatures, which are still very much unexplored. And potentially you can also do it with hydrogen air and methane air hydrogen flame to reduce that. And what you need are, of course, hydrogen again and very high temperature heat. So let's have a look at the reduction in fluidized bed. So in this case, you need hydrogen, we said, and you need also temperature. You need heat to provide temperature at 500, 900 degrees. At the mesoscopic scale, so the mechanism of transport follows this different step. So first you have the transport of the gaseous reactant from the bulk of your gas phase to the surface of your iron oxide particle. Then you have the diffusion of the gaseous reactant through the pores of your internal surface. Then at the surface you have also the pore, you have your reduction of the iron oxide, and with that you see the formation outside, on the outside layer, you see iron formation, while inside you still have, in this case, a bauxite. And then the product, which is, of course, water vapor, needs to diffuse back from the pore to the external surface. And then you have the last step, which is the transport of the product from the external surface to the bulk again. And then where you end up is, again, what I showed before, a very porous structure of an iron particle. If we look into the reaction, we have different reaction step. We have below 570 degree, we have what we call two-step reduction, and above we have three-step reduction, and this is because bauxite is stable only above 570 degrees. And below we don't form any bauxite. So by literature, if we look at the reduction degree, that's something that for example, in this case, we have 700 degree of temperature of reduction. So we are above the 570, which means that we are forming bauxite. And in this case, my reduction proceed over time, and I'm able to reach 100% conversion after a certain time. If we look at the reduction rate, we also see something interesting, which is that the first step is very fast. The first step of the reduction are very fast. So the hematite to magnetite is very fast, but the last step, in the last 80% actually of your reduction, it's a very slow process. So that is why this reduction can take a longer time. So my colleague Konrad Hessel, who is also an assistant professor in my group, did a TGA experiment. We put the powder in a crucible, and we let the hydrogen flow through it. It's a static bed, and you see that he did this for a different temperature, so 500, 700, and 800 degrees, and a different hydrogen concentration. Of course, when we provide a larger amount of hydrogen, our reduction rate is faster. And however, what we see is that at the high temperature, we can also reach a high conversion rate. However, it seems that the second step is very slow. And this is where the diffusion comes in. So that's really the limiting step, together with the formation of the very fast of a very solid iron layer on the surface of our particle. Moreover, if we go at a very high temperature, at 800, we can also see sticking of particles. So they start to create a solid bridge, and that's what the characterization, the analysis, the SEM images showed also, even from these, even here you can clearly see. I think that that wasn't done here and was neglected, because it was, of course, in this case, it was not important. The amount of water vapor could be neglected in the TGA, because it's a very peculiar system. You are removing all the water vapor very effectively, and you have a limited amount of powder. However, can we really say that we can neglect the water vapor and in a practical system? What is it really depends on the design and the condition of your reactor. If we look at the thermodynamic plot, we can really see that, especially for lower temperature, because we are talking about equilibrium reaction. If we are doing reduction at a lower temperature, if we increase the water vapor content, we end up to shift the reaction towards the magnetite and not towards the iron. So we are actually then we shift the reaction toward the hydrogen and magnetite production. And so that tells us something, of course, that if we are able to remove the water vapor, if we work with excess hydrogen, we're doing the things correctly. But if, for example, we recirculate back our hydrogen and water vapor stream, and we don't do this in a good way, and we therefore reintroduce some water vapor, well, it means that we didn't optimize our fluidized bed, and even a small amount of water vapor can have an effect on our reduction kinetics. And that's indeed what we have seen with other TGA. So this is again, you can see at 500 degree temperature, the conversion at different partial pressure of water vapor over the hydrogen. And you clearly see that if we increase the partial pressure, you have a lower conversion because, as I said before, we are talking about equilibrium reaction. And here is the same message. So if we increase the partial pressure of the water vapor, we are decreasing the conversion, and this is even more true for the low temperature. And because you see here the larger temperature, there is a decrease, but it's not as much as you see the decrease for the 500 degree Celsius, and this is indeed expected from the thermodynamic data. Okay, this is all interesting, but there is an elephant in the room, which is the issue with the sticking during the reduction of iron oxide, both in the fluidized bed as well as the shaft furnace. So that's a persistent challenge in the fluidized bed reactor, which is indeed the sticking. So the clustering of the particles that are sticking together. And what in practice do we see? Why do we don't want this sticking? Well, because we can have defluidization at high temperature. And so what we usually do in the fluidized bed is looking at the pressure drop over time, so the pressure difference over our bed. And if everything goes well, we have a stable fluidization. If something starts to go wrong, it means that we are experiencing some sticking, and we see a certain drop of unstable fluidization until we see a very fast drop, and that's where we reach defluidization. In this situation, it means that our bed is not moving at all. So it's actually something looking like this. So you can see that this is a very bulky, a full chunk of the bed that is not moving anymore. And you can see here this part, which are the channels where the gas hydrogen is passing through and is not really mixing the powder anymore. And of course, you don't want such a thing in a really operational condition, because that means that you need to stop your reactor, clean it, and start it again, which is in a continuous operation is something that you don't want. So although this is a very complex mechanism, we looked a bit into that, and this is, of course, due to the interaction between the particles, and more about the balance between the collision forces and the cohesive forces. So cohesive forces tend to leave the particle stick together, and collision forces, they are forces they are the forces of collision. So if we have the cohesive forces that are smaller than the collision forces, then we have a stable fluidization. If the general cohesive forces are larger than the collision forces, then we have an unstable fluidization, which can end up also into a full defluidization. So again, my colleague Konrad Esel, during his PhD, did some measurement of these interparticle cohesive forces. So of this solid bridge, which is a formation of this neck over the particle, as you can see represented here by the schematic. So look into the strength of the cohesive force, which are proportional to the strength of the net and the length of this bridge. And then what we did following this equation, these are all properties of the material, and we did measurement at different temperature and at different sintering time or contact time. And you can already see here that the neck is growing, the neck is growing when you are increasing the temperature. So what we did was to make some crucible, so to make some sample in a crucible, so to let it under hydrogen. We did also nitrogen, but under hydrogen we let the particle sinter together, and then we did a compression test. So we measured then the force that was, we correlated then the force that was needed to break this sample. And then that was a measure of our cohesive force. And we found that while the time of sintering, if we did a perform experiment for 30 or 60 minutes, it didn't have really a large effect. The temperature has a very as a dominant effect, which is something that is really critical. The temperature, indeed, for this problem, it's indeed very critical. So we did also, to finish up with this, with the fluidization part, we did also some reduction conversion. You can clearly see we did the reduction experiment for 1 hour at different temperature. And we did it also at different UMF, so increasing the flow rate, increasing the fluidization velocity. Like you can clearly see that all these red points are experiments where we experience unstable fluidization, and which end up in some cases are ready to full defluidization, while we are only at 500 degrees, we have a still stable fluidization. So we have a map in which we have here the cohesive forces are larger than the collision forces, and here the cohesion forces are lower than the collision forces. So then we see that indeed we can do experiment, or we can avoid defluidization only if we stay at very low temperature. However, even if we avoid it with fluidization, agglomerates or cluster of particles are formed. And so we always form on the microscope, or at the level of the particle, we always form some agglomerates. So the question then was okay, and can we recycle such a powder? Because our powder needs to go through a cycle of combustion and reduction. Can we handle this powder in the way that we can perform multiple cycles? So we did this. We did first 3 cycles of reduction and combustion, and here you can see only part of the result. You can see the particle size. This is the initial particle from where we started, and then we did a cycle of combustion and reduction. So C1 is first cycle of combustion, first cycle of reduction, and so on and so forth. And indeed, we see that there are changes. Of course, there is agglomeration in both combustion and reduction. However, it is still an acceptable distribution because we have if we measure also, if we calculate also the span, this is lower than 1.5, which is related to relatively still acceptable flowability. And then what we also saw is that we had an average storage efficiency of 83%. And this was really the first trial, the first 3 cycle that we did. Here you can also see some SEM images and even the cross section when you can see the porous structure of the reduced powder. However, we've seen that we couldn't reduce fully. There was still some oxygen in some particle, while others were fully reduced. We didn't stop here. We also did a 10 cycle then in a follow-up study. And here you can see the composition for both the recycled, so the reduced iron and the combustion product. And you can see we were mostly interested here on the stability of a different cycle. And here you can see that we could maintain a certain conversion, so a certain iron composition in our reduced iron, and the same if we can say for the combustion product. So we don't observe any large difference in the composition from cycle to cycle. The same is for the stability of the flame, for example. From a first cycle to the 10th cycle. And that's it for the fluidization, but I still want to tell you something about the flash reduction, which is indeed the reduction at a high temperature, which we are studying because that has the potential to reduce in the order of a few seconds. So that's why we are looking into that. And as I said previously, we are building our drop tube, so we don't have any things done in this sense, but we have done some modeling, some theoretical understanding of what could be the design of a reactor for such a technology. So here you see from the postdoc that Professor Cheng Mi and I are supervising, can see here the drop tube schematic. So here we introduce a single particle of our iron oxide, and we introduce fuel and air. In our case, is a hydrogen or a hydrogen methane and air flame. Here the particle is falling down in the drop tube, and it's falling into a flame. Here we have the premixed flame, and here we have the burn gas, and this is the length of our reactor. We are doing this in an invariant Lagrangian model and 1D flow. And also we assume that the particle doesn't have effect on the gas, since we are really considering one particle at a time. We're also using the reduction rate that are available. There are again few. There are limited study in this sense. And what we did first was to define a regime map for this hydrogen air flame. So you can see the equivalence ratio and the inlet temperature here. So if we are below in this region, in this orange region, a reduction is not possible because the partial pressure of water vapor would be too large. And then we have, again, for equilibrium, we will shift reaction to the opposite side that we want. In this region, in this green region, well, the reduction is possible, but the temperature is above the melting temperature of iron. Therefore, we don't have any kinetics available in literature. While in this blue region, we have the kinetics that are available. So it means we can do something with that. It means that we decided to simulate only this part, and with this model, we could really predict what was the reduction degree, simulating again this region 3. It is this region on the top with inlet temperature and equivalence ratio. You can see that you can reach higher reduction degree, of course, at higher temperature and higher equivalence ratio. So this is a model that can be used to, for example, look at predict what will be the reduction degree of a particle at the end of the drop tube reactor. But it can also help in designing the new reactor. It can tell us, for example, what is the length that you need to have for a specific particle to be reduced of a certain reduction degree. And of course, what you can already imagine, if you decrease the size of the particle, you can reach a larger reduction degree within 1 meter, at least for this graph, is 1 meter of the reactor. And this gave us the idea for a very, very preliminary experiment, but I thought it was nice to share, because why not sharing new things? So we chose a very, very small particle. So we don't use a drop tube because, as I said, we still don't have our drop tube. So we introduce some very small particle of the order 1 micron into this flame. This other reactor. So we introduce also hydrogen and air. And here you can see the powder before reduction. That is, we have a relatively broad side distribution. And here you can see the powder after a reduction. So you can see already here that it has some melting, because you have also very spherical particle, and you also see some sintering from these other SEM images. And we did also some ADS, where at the surface at least we could find some Wustite percentage. So that means that there was some indication of a reduction. Of course, this is a very, very preliminary. But that's indeed a sort of initial proof of concept for this very fast reduction process. I have still a little bit of time to also introduce actually another topic that mainly my colleague Professor Yali Tang is doing, is electroreduction. And you can see here a very beautiful image of the crystal deposit that you can produce with this technique. So briefly, just to mention what we first started with the very simple electrochemical cell with the hematite. That's why you see that it's so red, and we could obtain a certain dendritic growth with time. So you can clearly see that with time, we have a certain growth of the deposit, and here you still see red because it's not clean and dried. And the final, you see really the final product where when the cathode is clean and dried, I can see the dendritic growth especially on the side. This is really iron. This is and that's what we also see here from the same picture of the cathode. And if we have a SEM image, you see really the formation of these dendrites, which have a crystalline structure. We also know that we can a bit tune this crystalline structure depending on the condition in which we are doing this electrochemical reduction. And from what you can see here, again, we have EDS, and you can see that it's mainly iron. So we are really able to deposit iron. So if we look into, well, this is really an example of what this in the video of how the deposit are harvested. So these are really the dendrites that are produced, and you can see that we are just scraping off this iron that is produced, and with under certain condition we can reach a current efficiency of 80 to 90%, which is actually a very good current efficiency. And just to give, because I don't want to talk that much about this, but just to go through some pros and cons. Well, the pros is something I already said. We are using relatively low temperature. We don't go above 100 or 110, and we have a shorter production chain because we don't need hydrogen for this technology. However, we are still currently at a low TRL, and then we also need, if we think that this iron deposit need to be reintroduced in the combustion, we need a very optimized harvesting system, and then again formation of particles that can be introduced in a burner where we can combust them. So these are really a little bit the disadvantages for this technology. And I mentioned also before that we are also looking into the continuous production of this iron powder, because of course electrochemical cell, you can use it, but then there is the need of this manual harvesting of the powder, and we are looking into a solution in which we can do production and harvesting in a semi-continuous way, let's say. So that's why we introduced the concept of this rotating disc reactor, where part of the disc is for a certain time immersed in our alkaline solution, suspension, and then on another time, this iron that is deposited on the disc the disc can simply turn, and then it means it gets out from the solution, and the deposits can be harvested in this way. Okay, and then I think that brings me to my key messages for today. So again, I think that we need a comprehensive investigation of all available reduction technology. So my recommendation wouldn't be to exclude some of this technology, and why I'm saying that is because also these entire fields share some fundamental scientific question that if we know more about all this technology, we can know more about their reaction mechanism, their chemistry, the microstructure formation. So therefore, we are just addressing fundamental scientific questions which are common in this on this topic. And and as I said, I think that as a scientist, as a researcher, we have really the responsibility to explore different technology instead of just fixating on the sharp furnace, because that's what we know and that's what we are gonna do for the rest of the year. But if we really want things to change and to reach a higher TRL, it means that we have to invest on it, and we need to invest the time, researcher, and money, of course, on it. And last slide. So what we are doing now, as I said, I'm not alone in all of this. There is a group of PhD and colleagues that are working on this. For the fluidized bed reduction, we're still looking on the optimization of the reduction in a fluidized bed and on scale up of the technology. We are also looking at other cost-efficient feedstock in a project together with Professor Cha-Cheng Mi. We are going to do combustion and reduction of different feedstock to see if they are feasible for the iron power cycle. For the flush reduction, as I said, we are developing this drop-to reactor where we're going to investigate the kinetics of the reduction at such a high temperature in a very controlled system. And for the electrochemical reduction, we are currently doing some dedicated experiment to really identify the electrochemical mechanism of reduction, which are currently also limited in their understanding. So yeah, this is it for today. I didn't go so long in time, so happy that I managed in the time that was assigned to me.
Thank you very much, Dr.